Object-oriented design questions are one of two types of design questions in a typical programming interview, the other being system design questions. A typical object-oriented design question could be something like, design an object-oriented parking lot. Of course, we all know what a parking lot is, but we don't really think of a parking lot in terms of an object-oriented system. So a question like this can look very intimidating. But the key to an object-oriented design question is to realize that object-oriented systems communicate in ways very similar to how we human beings communicate in real life. So if you go to a restaurant, there's a server who is a subtype of a human being, obviously because a server is a human being and a server essentially has all the properties, all the behaviors that any other human would have. And obviously a server has some specialized behaviors too, like taking an order, bringing you food that a regular human being would not do. When you go to a restaurant, you have the server here and you place an order to the server. You don't really care how the server is going to get your food, whether he's going to go tell the chef, he's going to go do it himself. You don't really care. You just wait for the food. In fact, object-oriented systems communicate in very similar ways. So there are classes like human beings, subclasses like server, and when classes communicate with each other, they hide the details that are not necessary, that need not be exposed. So a class customer would call, place order on the class server, but what exactly happens after an order is placed, that portion is abstracted from the class customer. Isn't this very similar to how we order food in a restaurant? And this intuition between how human beings communicate in real life and how object-oriented systems communicate in an object-oriented paradigm is essentially the key to cracking a design question. And once you have this intuition, once you're able to see an object-oriented system in a very natural way, questions like this are just a piece of cake. So let us now look at how we could design our object-oriented parking lot. As a first step, when you are presented a design question, you need to ask clarifying questions. It could be something as simple as, what do you want to park in a parking lot? Is it a parking lot by parking lot, is it something for trucks, for cars? Is it a public parking lot, a private parking lot? Verify your assumptions, ask clarifying questions, if any. The next step would be to identify the major entities in the system. So in case of a parking lot, who are the major players? Obviously, let us say we are just building a parking lot for cars. So the major players would obviously be cars. And where do you park cars? In parking spaces. So parking spaces. And the parking spaces are a part of the bigger parking structure. So I would say the major entities are vehicles, parking structure, parking space, and so on. You could add payment system if it's a private garage. Maybe you could have a validation system and so on. But just to keep things simple, vehicle, parking structure, parking space are for now the major entities in our system. All right. So once you have the major entities, your next step is to define their behavior, or rather just identify their behavior. So what is a vehicle? Like what behavior would every vehicle have? Obviously, if it's a vehicle, every vehicle would have a license plate, a license tag, and it should also have the ability to move. If not, I wouldn't call it a vehicle. So the next step is to basically write down your entities and their high-level behavior. And in this case, for vehicle, the high-level behavior that we have defined is to have a license plate and the ability to move. So I use an interface here because An interface is very similar to a class, but I'm not actually defining what happens when you call the get license plate method. All that I'm saying is a vehicle should have these properties. I'm not really telling what these properties are. So this is why I use an interface here to just tell what behaviors my entity should have. So now if I have all my entities and their corresponding behavior, the next step is classes, where I actually tell what a behavior should do. What do you mean by get license plate? What exactly is an entity supposed to do for that particular behavior? So I'm actually defining the behavior that I have previously identified. So for example, there's in vehicle, I basically identified some behavior, and car is a class that implements a vehicle interface. Basically, I'm saying that car is a vehicle, and car is a class, so I can't just get away with identifying the behavior. I actually need to tell what this behavior should do. So car basically has all the behaviors of a vehicle. It can also have some additional behaviors, but car is basically a blueprint, a concrete blueprint of a real life object. So if you create a physical object like this, here I'm actually referring to a car in the physical world, an actual physical, a tangible physical entity here. And the behaviors of this tangible physical entity is defined here in this class. So that's pretty much our basic hierarchy at a very high level. We have interfaces, and then classes, which are a concrete blueprint, and actual tangible entities of these classes called objects. So now we have asked clarifying questions, verified our assumptions, and then we identified the major entities. We identified their behaviors through interfaces, and we also actually defined them through classes. But some of these entities can have some specialized behavior. Like, we all are human beings, but then a customer in a restaurant behaves differently than a server in a restaurant. So obviously a customer and server don't exactly have the same behavior. So another example could be, say there's a class vehicle, and there are buses, trucks, and cars. They all have the ability to start, stop, and turn. They all have this ability, but the way a car starts might be different from the way a truck or a bus starts. Maybe the engine, the mechanical components might be different. The same thing for turning. The ability to turn, the turning radius and stuff like that might be different. So while all of them have these behaviors, the exact behavior may vary from bus to truck to car. So I take my class vehicle, and I use inheritance to define each of these subtype of vehicle. All of them are vehicles, but each of them can redefine some of these properties. And then again, you could have subtypes of these subtypes. You could have an electric car which has some special properties like charging, which a mechanical car would not have, and a convertible car which again could have some special properties like to open its roof. So a convertible car has all the properties of a regular car. In addition, it defines its own properties. So that's essentially the next step, is to identify the subtypes of these entities, and we define these subtypes and their specialized behavior through inheritance. So the internet is full of examples of inheritance about animals being the parent class for dogs and cats, or vehicles being the parent class for buses and cars. But for a second, I wanted to look at a more concrete example, an example that you would actually use in your professional coding, and how inheritance plays a role here. The code on the top and the code on the bottom is exactly the same, except for the type of set that's being created. So when you call get set here, and the code on the top and the code on the bottom returns you a set object. But again, here is where inheritance and polymorphism plays a role. The actual set object that's being returned on top is a tree set, while in the bottom it's a hash set, the actual set object. But again, the code otherwise is exactly the same, and it operates on a set object. The code is not dependent on whether it's a tree set or a hash set. However, the behaviors exhibited would be different. For example, you could see that for the same code, depending on the due to polymorphism, depending on the underlying object that set points to, elements could be accessed either in ascending order or in no particular order. Likewise, looking up an element could either take log n or constant time, again, depending on the underlying set object that you're calling on. So, so this is probably a very classic example of polymorphism where, depending on the underlying type, the same object, the same set object exhibits different behaviors. So that is a small digression just to look at a more concrete example of inheritance. So let's move on and let's continue to identify our other major entities. Obviously, the parking space, that's where you physically park your car. A parking space could be, say, of multiple types, like we have a regular space, we have a compact space, and then reserved space for handicapped customers and so on. These are again subtypes of the parking space entity. And as we just discussed, we identify subtypes through inheritance. And then the parking structure. The parking structure is the overall building that holds these parking spaces, the overall structure. And yeah, and that could obviously provide some functions too. Like in some parking structures, you go in and the parking structure would tell you where to park. Or if it's a private garage, the parking structure might need to validate you before it even lets you inside the structure. So as we just discussed, we have parking space. And there are two types of parking spaces, say the regular space and handicapped space. So I use inheritance to identify its subtypes. So as you can see here, the parking space provides some basic methods, some behaviors that let you park a car. So when you park a car, you're given a certificate. And when you want to unpark your car, you give the same certificate, the digital signature, just to make sure that you don't walk away with somebody else's car, and so on. So these are the behaviors that every parking space would have. However, the exact amount charged, the hourly rate, that varies from a regular parking space to a handicapped space because we are providing a discount to our handicapped customers. So we use inheritance, and these are the child classes of parking space. They have all the other behaviors as the parent parking space class, but the hourly rate is different for regular space and handicapped space. So, so now when you want to create an object, does it really make a whole lot of sense to create an object of the parent class parking space? So you have a parent class parking space and these two child classes, regular space and handicapped space. So would you ever want to create an object of the parent class parking space? I would say no, because an object is a physical, tangible entity that you could a physical object in the real world. In the real world, could there actually be a parking space that is neither regular space nor handicapped space? If these are the only two types of parking spaces that we have? No, right? Our parking space should either be a regular one or a handicapped space. Moreover, what about the hourly rate? The hourly rate is not defined for the parent parking space class. It's only defined in the child regular space class and handicapped space class. So if you were to create an object of parking space class, what would be its hourly rate? So it's not really appropriate to create an object for the parent parking space class. And here is where the concept of an abstract class comes in. So now that you have your entities and their subtypes mapped out, identify classes that are not ready to be instantiated. Parking space is a class that I think should not have a direct object. Every object should either belong to type regular space or a handicapped space. So here is where I would use the concept of abstract classes and make parking space an abstract class, just so that we don't create an object of type parking space. On the other hand, you could also prevent creating an object of type parking space by making it an interface and not an abstract class. But if you were to make it an interface, all these methods would have to be re-implemented in both the regular space class and a handicapped space class, which I think is an unnecessary duplication of code, because these behaviors are exactly the same for regular space and handicapped space. So we have identified our major entities, defined their behaviors, identified subclasses for these entities, like parking space and regular parking space, handicapped parking space, and so on. And we have defined the behavior for each of these subclasses, and so on. So the next question is, how do these entities interact with each other? Right? What is the relationship between all these different entities? How do they all come together to interact with each other to form the overall object-oriented parking lot? So there are essentially two types of relationship: is a relationship and has a relationship. Is a relationship is what we have been seeing all this while, that's inheritance. So is a relationship is the relationship between parent classes and its child classes. It's essentially used for entities that are subtypes of the parent entity. Like regular space is a subtype of parking space, and handicapped space is also a subtype of a parking space. So we use is a relationship or inheritance. But how about parking structure and a parking space? A parking space is not a subtype of parking structure. Rather, a parking structure contains parking spaces. So when a class just contains a reference to another class, we use a relationship type called has a relationship because it has a reference, has a relationship. And typically classes are not subtypes of each other. For example, parking structure is not a subtype of a parking space. Parking structure just has a reference to parking space, so it could pass some messages to parking space. It could invoke some behaviors on parking space. And let's actually see how this looks in some basic Java code. So as a first step here, I have parking structure, and it has references to a list of available parking spaces. So here is the has a relationship between parking structure and the parking spaces. At this point, this is a very simple garage, so I just have a very simple linear list of spaces. You could divide it into levels and so on. And once a vehicle is parked, I try to keep the mapping between I try to keep a mapping of my use spaces, just so that whenever somebody comes over and tries to remove their vehicle, I could identify that parking space, unpark the vehicle, and then add it to my available space. And these are all some generic methods my parking structure provides. So this would be a parking structure at a high level. And note that when I say parking space, I'm using the abstract class parking space. Or even better, we did not really have an interface for simplicity, but if you had an interface, it would be even better to use an interface there. But for simplicity, we just started with an abstract class for parking space, so let's just stick with it. By using an abstract class for parking space, I don't really specify whether it's a regular parking space or a handicapped parking space. So the exact behavior of the parking space would depend on the actual concrete class in that object. So we now have the parking space class, which could either be handicap space or a regular space, and handicap space extends parking space. Likewise, regular parking space too would extend parking space, and each one of them concretely defines the get hourly rate. So it's the has-say relationship between parking structure and a parking space, and is-say relationship or inheritance between parking space and handicapped parking space and regular parking space. So it helps to take a quick look between interfaces and abstract classes because they are sort of similar and could be a little bit confusing on when to use what. I would use abstract class basically to provide skeletal implementations, and I would try to use abstract classes to avoid duplication of code. Because if methods like park and unpark were to be implemented in both regular parking space and handicapped parking space, it would be a duplication of code. So I use parking space as an abstract class, which has all these common methods and specialized methods that inherit from this abstract class. On the other hand, I would use interface for basically as a first step to identify the behavior of my major classes. So I would rather first have a parking space interface that identifies the high-level behaviors of a parking space, and then an abstract class for parking space where I actually provide skeletal implementations for these methods, and then concrete classes of regular parking space and handicapped parking space, which have all the behaviors defined. And an interface can also be used to enforce some behaviors, as we can see. For example, if I only want to work with cars which have an auto parking feature, I could use an interface to enforce this. For example, in my garage, I only want cars which have an auto parking feature. This basically means that any car that wants to park in my garage should have the ability to park and unpark on its own. So I defined this interface called auto parking car, which should have the park and unpark method. And whoever wants to work with me would now have to implement this interface because my method only accepts an auto parking car. It just doesn't accept a regular car. So whoever wants to work with me has to implement the method park and unpark. This way I could be sure that if you're going to work with me, your car will have the park and unpark behavior. So now when I say parking space.park of BMW, it works because BMW implements the auto parking car method, the auto parking car interface, so BMW is an auto parking car. On the other hand, you can also see that the Honda guys haven't implemented the auto parking car interface, so it is not an auto parking car, and that would be an error. So this helps ensure that any car that tries to park in my space has the park method, and I could just call BMW.park. So here's a high-level overview of all that we have had so far. I did not really show some of these interfaces in the code just for simplicity, but we have interfaces for all our high-level entities: parking structure, parking space, cars, and so on. And as the next step to interfaces, we have classes or abstract classes that come up from these interfaces. So here we have some parking structure based methods. We have parking space, an abstract class parking space. We have a couple of more abstract classes here. And from these abstract classes, we have classes, concrete classes that further inherit from these abstract classes, right here and so on, and a few more concrete classes that inherit from these abstract classes. And lastly, related classes are inherited or related by inheritance, and unrelated classes like parking structure and parking space, they are related to each other using association. So this would be our high-level design so far. So our next step is to try to refine this model, sharpen it, and see if we could use any design patterns to make the model better. So let's quickly look at a few design patterns. So what exactly are design patterns in the first place? These are solutions to common problems that we encounter in object-oriented paradigms. For example, here we have a parking structure. But do we really want everybody to be able to create a parking structure? Probably not. In our city or in our system, we just have one parking structure, which we want people to use to park their cars, right? As opposed to, we don't want every car to create its own parking structure. We just want one parking structure where people park their cars. So how could you ensure that there's just one parking structure? So one way to do it is through a design pattern called singleton. The key features of this parameter are you make the constructor private, and you have a reference to an object here. A small typo, this object should have been static. This object needs to be static. So now you also have a static method that would be called by anyone who wants to get the parking structure object. You call getParkingStructure, and you can see that the only object that this method would return is this PS. So only the first time would you create a new object, and we will always be returning the same object. So this way you could make sure that there is just one parking structure object in the entire system. So in your go to your model, identify classes that you don't want to have multiple instances of, and make them singleton. Likewise, it's also possible to restrict some classes just to have k objects, and where this is a specialized case where k is 1. And then there's the concept of static factory methods. That's essentially the static method that we just saw to create a singleton object. But there could be reasons to use the static method even if you don't want to restrict the number of objects being created. For example, here, depending on the license somebody has, we give them a public parking structure or a private parking structure object and whatever. So the user or the third party using your parking structure class, they don't really need to know this entire hierarchy of public parking structure, private parking structure, and so on. So you have a public parking structure object, you have a private parking structure, and maybe your hierarchy is much longer. So they don't really need to know all these details. So by just providing this method, parking structure.get parking structure, all that they need to do is call the get parking structure object, and they get a parking structure object. The exact type of the object depends on this license. It could either be a public parking structure, a private parking structure, or whatever. The behavior, the runtime behavior would depend on their license, but they are totally transparent to it. They just, all that they need to know is to use the behavior defined in the interface or abstract class parking structure. It's very similar to the earlier example that we saw for inheritance, wherein you just call the get set method, and the actual set that's being written to you could be a hash set or a tree set. And then we have the strategy pattern. So let us say in our parking structure, we have a calculate payment system, an algorithm to calculate payment, and we would like to use different algorithms to calculate payments on different days of the week. For example, on weekends, the night, maybe we don't charge our customers for overnight parking, and maybe during the day for weekends we charge them a higher rate on weekends than weekdays, and so on. So one way to do this would be, you have a lot of if-else clauses where you say, if you're using this algorithm, use calculate payment using this formula. If you would like to use the weekend algorithm, use this formula. If you want to use the winter algorithm, fall algorithm, use this formula, whatever. You could have a bunch of if-else statements to enforce or to choose between a bunch of algorithms. However, another option could be to use the strategy pattern. Here what I do is, I totally avoid the if-else clause, as you can see here. All that I need to do is I just say algo.calculate payment. And depending on the algorithm object, this could be a weekday algorithm, this could be a weekend algorithm. The calculate payment behavior depends on the underlying algorithm object. The behavior of the calculate payment could either be a weekday algorithm, a weekend algorithm, or whatever. But I have totally avoided the if-else part here by just having an algorithm object, which could be one of the many different algorithms, and by just setting the right type of the algorithm object. So instead of having all this if-else, I just set the right type of the algorithm object. So the advantage of doing this is not just to avoid the if-else statement, it also separates the code better. It has low coupling because the payment algorithm class can be compiled separately, and you can easily introduce newer payment algorithm classes. It can be compiled separately, and so on. So the code has less coupling, and it's a lot easier to maintain, and it's more object oriented than having a bunch of if-else statements. So go to your design, look at any places where you have multiple options that you might want to change at runtime, and replace them with the strategy pattern. So that is essentially our very basic version of coming up with an object-oriented parking lot. So now I would ask that you follow these steps and try to come up with an object-oriented fridge.